Okay, my friends, this is a pulse of red laser. That is the very leading edge of the red laser. It is heading into a venturi. It is beginning to accelerate. That's the reason we're able to see it. Now, as it hits the venturi, the first thing that happens is the particle accelerates right out of the wave. A venturi is an accelerator, and that's what you have to do is particle acceleration. Then what happened? We created a restriction here that was so finely tuned that it would only let the white through, the black can't get through. That's, as I will show you right here, precisely what they wanted to see. The black balls by themselves, the white balls turning into showers. And here they are, coming through the venturi. The black muon neutrino went on its own. The white electron neutrino turned into a shower. Precisely, this is from CERN or Fermilab or whoever, that's not mine. That's exactly what they want to see, exactly what we did. Okay, just so you get an overall picture of what's going on. I showed you the pulsed red laser, the leading edge. I showed you the acceleration and the particle division, which is what CERN wants to see, the muon neutrino, electron neutrino, which is this black and this white shower. And just as they're concussing, they go through a neutrino phase. You see, this is the same particle as this, only it's in its neutrino phase. It's just starting to concuss and gain energy. So that's why they say they change flavors. Well, they change energies. These are the actual photons, and then they collide and they actually combust, they break apart. And that's the only particles, as far as I'm concerned, that can turn into just a black and a white ball is down in this realm, because other than that, you cut a bar magnet, and that's all it is, a bar magnet. You cut a bar magnet in half, you get two bar magnets. Well, we can cut the white from the black. Okay, I'm going to make this as not complicated as I can possibly make it. I showed you that we actually found these particles that they talk about at Fermilab. We found them. They do exactly what they said at Fermilab. I have no argument with that. We created those same particles that I showed you right here at Fermilab in the venturi. And the venturi created these particles. Hold on one second. Okay, these are the black and the white showers. These are the fixed particles. These are point particles. Look it up, point, what is it called? What's the Point by Fermilab. And it shows these are the particles. This is actually copied from that paper. As a matter of fact, I have the paper here somewhere. Here it is right here. And maybe I already showed it to you. But anyway, this is the paper, and these are the particles. And they do exactly what they say. One of them is a bowling ball. One of them has no mass to it whatsoever. And they react that way, too, when they hit a house in an atomic bomb blast. So we found those particles, and they are attached together in light. Light is an elementary particle. That's the elementary particles they found at CERN. We did it using a venturi to crush the field sideways. So you don't have to hit them head on. If you can force them to crush sideways, and we can, and the reason I believe a lot has to do with it is the black particle, because the black particle literally pushes the white particle, and I can show that as well. And this is what they are looking for right here. Whoops. Is these muon neutrinos, which is the black ones. They just keep going by themselves. They separate from the electron neutrino. So remember these two neutrinos. Remember neutrino. This turns into a shower. It's exactly what it does. Now, I said neutrino. Well, what about this? Where is our Dirac? Here they are. These are Dirac neutrinos. And they show the same thing, matter, antimatter. And as they're flipping and so forth, they can see them in a Majorna. They see them spinning and things. But I can show you these particles. And a Dirac neutrino literally is what we would always consider an electron. That's the glowy part of the electron. But it gets carried and pushed by the dark particle. And pushed and sucked, both ways. It does them both. And that is that particle, which is this particle, the Dirac neutrino back to back. See them? There's one here and one here. They're just like bar magnets. And we can split those, which we did. There's no question about this. They were here together, and there's the particle, and then they split. Can I show the particle as its own particle? Yes, here it is. Can I show it in a stream? Yes, I can. Here it is right here. That's the neutrinos starting to gain values, changing, flipping sideways. See them this way here, then this way here. They say they change flavors as you're driving home with with one type of ice cream, supposed to be vanilla, but it changes to chocolate and then strawberry and then tutti frutti and whatever. By the time you get home, who knows what it is. But here's the way it happens. It stacks up against itself and it gains energy and then it explodes. Got it? That's how it works. These are that particle that I'm talking about. This is the particle. These are photons. When they're in this phase, that's a neutrino. It doesn't have the exact equalness of a photon. And you know what? Here, I can show you. They can see these particles. I'm not making any of this stuff up. Where is it? 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 I think I don't have it. Oh, there it is. There it is. Everything's somewhere if you look long enough. This is the particle I just showed you. That's it. They see them. And then they see these can break away from these, which I showed you, the white and the black break apart. Then they can see big chunks because they're breaking big, huge things together. They're taking big, big, big balls of things and they're smashing them, and they're just every kind of debris you can think of, and that's it. And they call this the particle zoo, and they think all of these are elementary particles. They are not. This one and that one are the two elementary particles. Everything else is made of those. Some of them more intense than others. These are the photons. You can break away particles, the blue, the green, and the red. You see those three colors? That's the three colors. And we have them do this. All of my experiments had the same stuff, three colors. And you can see that the things that I'm talking about are shown in, this is another one of CERN's things, but they're showing they crash this and have all this debris, and they pick through it for years, literally years, hundreds and hundreds of people, and just to find what we could squirt out of here all day long, which is these particles right here. All right, that is the light accelerating, and that is that particle I showed you, the black and whites, two side by side, look like bar magnets. Here they break apart, that's fission. Here they come back together, that's fusion. Here is raw energy. As far as I'm concerned, I don't see why it isn't. And here's what it looks like when it smashes back into reality. Look at that. That looks pretty serious to me. I don't know if this is just from a tiny little light, a little cheap construction laser that pulses, boom, 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 boom. And what I think happens is here at the Venturi, here's the key to the whole thing. You need this stuff squirting through here violently. Now, if it just hit here and there was just a tiny little slit, that'd just splatter off. But no, we've got this black smacking, and it's smacking hard, and I can show you that as a fact, because it forces a whole wave like this to accelerate in front of it. I'll show you that in a second. Well, right now. All right, remember I showed you before the black and the whites together? Well, this is coming through the Venturi where they have become separated, and the black is pushing the white forward in really violently, so it pumps up and glows. That's the nature of it. Now, can we do this? Can we take a Venturi similar to that, and I don't know, that little bit black through, maybe yes, maybe no. The other one had no black whatever. It was 100% white. This one, some of the black came through with the white and is pushing it, and that may be preferential. I don't know. These are things that have to be tested. We need a lot of experiments. But if we can push that into a solar collector, nothing more than like a solar panel, right here, right there, and just push it, squeeze it into there, and it's being pulsed. You see them, bam, 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 bam. So where does this have to go? It's got to go somewhere. We'll drain it down through a photodiode. Because if this is like a brick wall coming at it continuously, and you can vary the intensity of the pulses. Maybe it's slower, maybe it's faster. I don't know. Maybe it makes a big difference between red or green or blue. I don't know. But that's all the testing. But if we can squirt this stuff down through a photodiode into a battery or a device, whatever, and then use a little bit more to come back to keep the laser going back here, which is running cheap, and then put this inside of a little handheld device like this. All right, you have thousands of these lasers in there, thousands of them, collecting whatever current you can collect out of them. I don't know. You may even not need thousands of them. I have no idea. But inside here, you'd have to have a couple little regulators, so you could have any type of electricity you want. It's different cycles, different voltages, AC, DC, USB, whatever you want. And just carry it around. Watertight. Carry them up. You plug your devices in for fighting fires and pumping water and lighting lights and disaster areas. If it works. I don't know if it'll work or not, but I'm seeing energy. And when I show you, or I maybe did already, about what happens with electron showers, it looks to me like it's the key. Other than that, you're working with protons. Protons don't have the electron energy. It's electrons you're looking for. You're looking for the electrons. All right, so let's talk about free energy. Remember I talked about these gigantic particles hitting head on, and just very hard to do that. And secondly, it's nothing portable. It's nothing you can carry around. These are heavy particle colliders. We're using light, just laser light. We just did this, and like I say, you could do that in that little box I showed you. Now, what does that lead to? It leads to a possible creation of the physics of electron showers, which is, as I said, that's what you're looking for, is electrons and muons. That's what we need. And you need to create neutrinos to make these electrons and muons. Remember the neutrinos I showed you? They were using proton-proton collisions to create what they call hadrons, and then a secondary collision and decay to create high-energy neutrinos. And then the neutrinos created the electrons and muons. The energies of neutrinos interacting within that device they created, which is just unbelievably complicated, range from 100 billion electron volts to a few trillion electron volts. That's because they're getting electrons and muons separated. And that's at the lowest possible level. And we did this. We created the neutrinos, and which were from the electron, or the neutrinos, electrons, and muons. They're all the same. The neutrinos are just a different crushing value of these electrons and muons. Neutrinos just keep changing flavors. It depends on how hard they're hitting. That's the key. Neutrinos are never settled into a certain energy. It depends on what they're hitting and what their energy value was when they started. All right, here's the problem. They really don't know much about these neutrinos or light at all. They say they can see 3 different flavors of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. And they all have different masses, even if we aren't sure of exactly what those masses are, or which flavor is heaviest and which is lightest. They really have no clue, because they don't. The standard model does not really account for this in a correct way. You have to get into dipole electron flood theory and actually see them divide into the electron neutrino and the muon neutrino, and then create the showers. This is all predicted, and they have seen this in their gigantic colliders, but it's just debris. So that they really don't know how to put the pieces together. We started with one coherent frequency of light: red, blue, green. And then we can watch that manifest itself into photons, muons, neutrinos. We watched the whole thing happen. just using light. Once you get into these protons, you're just in a mess. You're just in a pile of debris. Okay, my friends, at all the particle accelerators, they use proton-to-proton collisions. Well, the physics of electron showers is much better. And what it does is creates neutrinos and electrons and muons, and they are from 100 gigavolt electron volts, which is billions, to a few trillion electron volts. When you can separate the electrons and muons like this, instead of using proton-proton collisions, you get extremely high energies. And that's what we did. Okay, my friends, consider this. We all know a solar panel takes light, it's literally light, and hits it, and it turns it into electricity, because they are electrons. So light is literally made of electrons. So a physics of electron showers very much exceeds the physics of proton-proton collisions. Electron showers are what I will show you, and they create 100 gigavolts, electron volts, to a few trillion electron volts, depending upon the interaction of the neutrinos. And we're working with electrons and muons. Let me just show you exactly from CERN. We should be able to use this. I don't see any reason why not. All right, we're going to look at some of the light experiments in a minute, but one of the key things they're missing is if that light is slowing down, what happened to the energy that was making it go real fast in the first place? Can we harvest that energy? I say yes, we might likely could, through a device like this. We create this, we did something different than they're doing, but the point is they're slowing the light down. What happened to the energy that was pushing the light in the first place? Can we harvest it? Yes, I believe we can through a device like this. We can catch this white before it comes back to being part of the natural landscape. And maybe we can put these in here and have a portable free energy device that you can walk around with. That's increasing the energy. There's no question about that. And so what happens to all that energy? Because now the light is going to be slower. We filtered this down. It's slowing that light down. And I mean, it really is slowing it down. So what happened to the energy that was pushing it in the first place? That's what we want to capture, is that energy. Okay. What they did here is to proton-proton collisions to strip electrons away, creating neutrinos and antineutrinos of electrons and muons. And those neutrino values are in the gigavolt to trillion electron volts. All right, you see this? This goes back years ago. The Large Hadron Collider, they wanted to use it as a photon collider. They couldn't figure out how to do it. This goes back to 1978. They had a special commission to try to figure it out. The Large Hadron Collider smashes protons, and they get high energy particles, but they're using hundreds of billions of particles, and they send them head on, and I hope some of them will hit each other, and only 25 or so out of 100 billion will hit each other. So it's really not a very good way to do it whatsoever. So they wanted to use photons, but they couldn't figure out how to do it. So the physics case for photon collisions. Physics of photon collisions has been a topic of some interest for many decades. Indeed, a special meeting in '78 discussed the prospect of photon collisions. They wanted to do them head-on, couldn't figure out how to do it. The LHC predecessor collided electrons with positrons, But they did a special, where is it? Somewhere down here. They did it in 1978. They had a special meeting. Hold on a second. Okay, my friends, this is really kind of amusing, actually. They wanted to use the Large Hadron Collider as a photon collider, and they really couldn't figure out how to do it. This goes back to the case for studying photon collisions. That's what I'm talking about, is light. Light is photons. You stay away from the big gigantic particles, which they were using hundreds of billions of them. Look at this. They were using 100 billion particles at a time trying to hit some head on. Only 25 or so hit head on. We used a whole new style design. Instead of hitting head on, we crushed them sideways. Very, very simple and very effective. But the physics of photon collision has been a topic for some interest for many decades. A special meeting in 1978, they had a special commission on this, discussed the prospect of these collisions. And they couldn't figure it out. He says the collisions are very clean as we're colliding photons, which are elementary, the tiniest particles there are, and not comprised of big ones like protons. They're huge. They're just gigantic compared to what we're using. And this person who was heading the project. It was first proposed to do this type of physics at LHC when CERN many years ago, but the project didn't materialize then. They just couldn't figure out how to do it. And all you have to do is crush them sideways. You don't have to hit them head on. You see this right here? This is what everything at CERN is about. Everything they're doing is about creating sterile muons, which is the smallest dark particle, and electron showers, which I'm just talking about right now. Photon electron showers is very, very powerful rays of energy. These are from these two neutrinos. We've been talking about neutrinos. Just keep your attention on the fact that there's muon neutrinos, which are the black ones, and there's white ones, which are the electron neutrinos. They glow and all that. This is a fixed particle. That's what they call a point particle. It can get big and get small, and they can create showers. And these are where all the energy is. These are like bowling balls. They don't absorb, they don't emit, they don't reflect. They're just, this is actually dark energy. It literally is dark energy. So they've been looking for it forever. It's the muons. They hold tight to an electron. They're called Dirac neutrinos, the two neutrinos together. Now, this is what I'm talking about right here, is accelerating the light, because we have a Venturi squeeze and crush the fields together, and then because you have the black bowling balls coming back, they slap and bang and slap it through, squirt it through here like a squirt gun. And this is extreme amounts of energy. Anytime you see this kind of luminosity coming from non-luminosity, that's an increase in energy. And this could very well be the holy grail of energy right here, being able to carry around in a little lunchbox. Okay, I just want to show you something. If you got any idea about physics, you've seen Feynman diagrams in profuse quantities which show the interaction of particles, of energetic particles. Now, what do they have to say about this at Yale? I went through the Yale quantum courses just to see what they had to say, and I will show you what they have to say. And I did go to University of Geneva for particle physics as well, and they didn't have much more to say than what he's going to say here from Yale. Let me show you what he has to say. Now, this is Yale. This is Professor Shankar, and they have courses. He's got like, I don't know, 15 or 20 different courses here, but you can go to almost any school for free. Literally, but you don't get any credit for it. You just have to go if you want to learn something or look into something. I'm going there to sort of confront people, because I'm going to tell you, here's what they have to say about quantum physics. And this is Professor Shankar, and I applaud him for saying what he's going to say. Listen.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now, I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So,
unfortunately, it's true, because he's just going to tell them what he's been told to say. He doesn't understand it. Feynman didn't understand it. And you see Feynman diagrams everywhere. Well, I think I have something to contribute. Maybe I don't understand it either, but I'd like to engage. And that is not I'm not allowed in this realm because I have too much evidence. So they keep me out. I mean, I'm serious. I would love to engage with any of these people. I went to the University of Geneva in Switzerland. I went online, not personally there, but I interacted with the professors and everything. I showed them my stuff, and they sounded like they were very impressed. And I said, well, let's do something. No, we'll follow you. We'll watch you on Facebook. And I said, oh, you got to be kidding me. I said, aren't you going to look into this stuff? No, we have things we're doing. And I said, well, okay. You know, they're right there with CERN. As far as I know, they were part of the whole package there, but who knows? It's what I have shown, I think, is pretty convincing evidence of working with the most elemental of particles, the elementary particles. That is where CERN, Fermilab, and all of subatomic physics wants to be, is at the particles we have, which is light, and breaking those particles apart, which is fission, and then when they come back together, that's fusion. You know, I've shown dozens of times how we did this. I literally, and this is all we use. Rod used the same thing as I'm using here. And he used this exact same phone, Samsung Galaxy S3, and this exact same laser to create these red ones, which is a GLM 15 Bosch. He used a metrical and doesn't make any difference. Now, he started out like this with 2 finishing nails, literally finishing nails, and shot the laser through it. And he ended up getting these incredible pictures. And I said, Rod, how did you do this? I saw it online. And I saw that, and I flipped out. And I could see the particle was accelerating. There's no question about that. And anyway, we worked on this for years. I mean, 5, 6, 7 years. And I've lost track of Rod, and I just hope he's okay. I can't get through to him anymore. So, and I did my own stuff here, but Rod was just stunningly fabulous. He must have put so much time into this, I can't imagine. But I did this with the screens. So I was getting this kind of an effect. And this kind here, where these were with screens. He was just using one slit this way, but it was a Venturi. Everything had to come through, and you could actually see the spinning light. Now, I could see the spinning light here, because as it spins, it separates itself out. That's what I was kind of interested in too. There's so much to think about here. But this was Rod's stuff. He was actually seeing the particles, seeing the neutrinos, seeing the black and the white particles. And the same thing was in the red, exact same particles. Right here, same neutrinos. You see? The little Oreo cookie looking things. See it? Some of them are white and black and white, and some of them are black and white and black, and some of them are like that, photons. So there's a lot here, and I don't remember where I was actually going with this, but when you go into outer space, the same thing. I'm not sure they understand what's going on out here, and they also don't realize that all of this space debris and all of the light, which is particles, is blocking the light from coming to us. It's not redshifted. It's just being slowed down by the stuff that's in front of it. As light slows down, I think I showed that, or will. There's no question about that. I think I included this earlier, but I got to be honest with you, I can't remember. Scientists slow the speed of light. This is back in 2015. They slowed it down. No question, they slowed it down, and it never sped back up again. They always used to say, oh, if you go through water or whatnot, it'll slow it way down, and then it'll come right back up again. Why would it accelerate? No, absolutely not. Anyway, I think I made a very good case for what I'm claiming. Now, I would like some physicists, not anatomists, astrophysicists, that kind of people, to speak. What am I doing wrong? Where is my mistakes? Where did I err, so to speak? Okay, my friends, this is why I got confused about whether I had shown you about the redshift and so forth before. The redshift is not correct. Light slows down. This changes everything. So I have a whole nother video coming out about it called the Redshift Dilemma Disaster, something like that. Because it is. It's a dilemma. It's a disaster for astrophysics. If light slows down and light is filled with particles, both of which are true, then we really have very little idea of where we exist in the universe. Because first of all, the universe is not homogeneous. There's globs here and globs there. And secondly, light does slow down. Right, this is what the universe looks like, or even our solar system. So if we're coming this way through whatever we're coming through, we could be plowing through who knows what. So this could be, well, it's certainly affecting our weather if we're going through denser space, because it's pushing to scrubbing. And I show that as well. I've shown all these things. All these things. Did you know that the sun is only 10,000 degrees on the surface? 10,000. You know how much it is way out there at the corona? Millions. And they have no explanation for that. None. Zero. Same with here on Earth. On Earth, it's, let's say, 100 degrees. Out here at the edge of the ionosphere, where it scrubs against all the rest of the particles in space, it's 2,000 degrees. No idea why. And then it goes down to minus 80, just below there. Wherever you have hot, you have cold. All right? And that hot wants to move into that cold. And that's what global warming's about. So stay tuned for the Redshift Dilemma Disaster. Now, I'm not coming into this blind-eyed here. This goes back to 1970. Even earlier than that. I was in the Army in Nike Hercules missiles in 1968. And this is all the different rules that you have to follow about Heisenberg and, Schrodinger, Pauli principles and de Broglie and all that. Now, then you go into all of the different laws and all of that sort of stuff and experiments and Millikan's oil drop and all that stuff. Then you start to get really deep into it. And then you get into bonding orbitals and all that business and da. And I went on through every bit of physics as far as you could go. And I came up with the conclusion here long, long ago that the transfer of energy is from light to atomic vapor. Light is literally atomic vapor. That's what light is. It's not, they say wave particle. It's both. It's a particle and it has a magnetic field around it. When it comes through, the field creates a wave. Simple as that. And there are particles in the center. And I did this as deep as anybody, as far as I'm concerned, has ever done it, and I'm still doing it today. So this is not like I'm guessing. Well, I'm guessing at something, sure, absolutely, no question. But it's based on a lot of research. I'm not just somebody spewing out some nonsense like this. Okay, I'm showing why I feel confident that I can speak in this realm. This goes back to a long time ago. The Army General Classification Test is GT test, and it's General Technical. Technical is a lot different than being, knowing all kinds of theoretical stuff. I do things with my hands. I'm a material scientist. Totally different than your other type of theoretical scientist. Now, General Technical, abbreviated GT, and if you scored 136 or higher prior to 1980, which I was in 70, I came out, and Mensa will accept the result as proof of being in a 98th percentile. So you had to be above 136. Well, let's see what I was. All right, I think I showed you that if you had above a 136, you were considered in a 98th percentile. I have a 139 GT. And that's from when I got out of the Army. Now, I continued on, as I showed you or will show you, and I'm still doing it today. That's just what I do. I never, I just like it.